So we're gonna talk about the new topic, Ostwald Dilution law. So what is the Ostwald Dilution law? First of all, let's classify it. It is only applicable for weak electrolyte. We generally study this law for weak electrolyte. So let's say we have a weak electrolyte. What is the electrolyte and what is a strong electrolyte and weak electrolyte? We have seen previously. Now we're gonna see, let's say A, B, we have a weak electrolyte in aqueous medium. It will be dissociating into A plus in aqueous medium and B negative in aqueous medium. So it dissociates like this. So at time t equals to 0, its initial concentration, let's say C. When time passes, its concentration reduces to C minus C alpha, and it came out to be C alpha and C alpha. It came out to be C alpha and C alpha. So what is the ionization constant? Means they are ionizing, like in the chemical equilibrium we have seen that KH, let me repeat, that is Ka and Kb we have seen already. Okay, Ka, Kb, Ka stands for acid dissociation, Kb stands for base dissociation, K forward, K backward. Now that is different. K. Now if we talk about Ka, let's say, so Kp, Kc, if we generalize the Kp, Kc, we haven't seen Kp and Kc. Here we will be see Ka and Kb. So that how Ka and Kb is determined. And rate of forward reaction becomes equals to rate of backward reaction, and the constant is called the equilibrium constant. Ka, Kp and Kc, right? But here, when the ion product are dissociating into ionic compound, which have been classified as ionic equilibrium, we have seen previously. So Ki is the same like concentration of product minus divided by concentration of reactant. So Ki is ionization constant of weak electrolyte. In this weak electrolyte, if it is acid, then it will be called Ka, and Kb we will be seeing further. But we have seen Kp and Kc, so it is relatable to Kp and Kc, but not exactly them. In Kp and Kc we use for chemical equilibrium, where they are not dissociating into ions, but here we are using it as a ionic equilibrium. Whose numerical value will be given in the problem. Means what does it mean? Whose numerical value will be given means experimentally determined, or with the help of the data we can determine the value, but we can't change the value. It depends on temperature, then we will later see, but generally the value of Kp and Kc are given. On moving further, what is Ki? Ki was concentration of A plus and B minus divided by AB. Let us C alpha into C alpha was the concentration of A cation, and B anion divided by concentration of AB was C into 1 minus alpha. So Ki turns out to be C alpha square divided by 1 minus alpha. Now we have seen, here we know the Ki ionization constant and concentration. What we don't know? We don't know the alpha. That is known as alpha. We don't know. That is known as degree of dissociation, right? So alpha is unknown. So, but we know whenever we are talking it as a weak electrolyte, we know it is negligible. Whenever we are talking about weak electrolyte, that means alpha is very less than 1. We can neglect 1 when we are adding or subtracting. We can neglect alpha when we are adding or subtracting to 1. So 1 minus alpha is approximately equal to 1. So ki will becomes equal to c alpha square. Now alpha becomes equals to under root of ki by c. So that is the Ostwald dilution law. That for the weak electrolyte, the alpha means degree of dissociation is inversely proportional to the concentration of the electrolyte. So as you reduce the concentration, the alpha will increase. Means it is a very good application. Let's say we have an acetic acid. We know it is a weak electrolyte. And first we have 1 molar. Now we are diluting it. We have added some water over here. Now let's say we have done the concentration. Let's say 0.5 molar. So we know it will be dissociating. It will be giving some H plus while dissociating into its respective ion, and it will also be giving H plus while dissociating into its respective ion. But the amount of H plus, the concentration, the alpha means degree of dissociation will be more in that case. Okay, we are not talking about K will be same, as we will say that depends on temperature only. Okay, but alpha will change. Alpha will be more in that case. So that we came the conclusion by the result of Ostwald dilution law. Now, what are the factors that will affect the alpha? Factors affecting alpha: degree of ionization. We can't say every time dissociation because we can say it's ionization, right? So first is nature of solute. For weak electrolyte, alpha is very less than 1. We know whenever we are calling it as a weak electrolyte, in degree of ionization will be very less than 1. It will not be completely ionized into its constituent ions. But whenever we are using a strong electrolyte, the alpha will always be equals to 1. Second, nature of solvent. So how do you affect that solvent will affect the alpha? So like solvent should be polar in nature. Solvent should be polar. We know like dissolves like. Whenever we are talking about the ions, we will be obviously dissolving into the aqueous, the water. So water is polar, and we know like dissolves like. So water will completely easily dissolve the polar solvent, right? So dielectric solvent, we will be using the water, right? Solvent should be polar in nature, like we use the water. So whenever let's take an example, whenever we have a solvent, let's say generally it is a polar, but whenever it could be polar and non-polar, let's say polar and non-polar. Let's take all the possibilities. Now we are dissolving any ionic compound, so that obviously is polar. So like dissolves like, polar will dissolve in polar. It won't be dissolved in the non-polar, so it should be polar in nature. Dielectric constant should be high. Dielectric constant should be high. So, water satisfied, both the properties. So, it is a universal solvent. Water has polar nature and dielectric constant is high. Now, what is dielectric constant and how does it help? You're gonna better learn in the electrostats of your physics. Now, next is concentration of electrolyte. That was we have seen the Ostwald dilution law. So first of all, let's say whenever we have a strong electrolyte, a strong electrolyte, alpha will always be 1. Alpha will always be 1. Alpha will be 100%. Alpha will always be 1, right? Now, whatever is the concentration, it doesn't depend what is the concentration. Alpha will always be 1. But whenever we are using a weak electrolyte, so alpha is inversely proportional to under root of concentration. So as concentration decreases, alpha increases. As the concentration is decreasing, the degree of ionization will increase. So what in extreme case? In extreme case, let's say alpha, the concentration is tending to 0. We are keep on the condition of infinite dilution. When I keeping the dilute, the acetic acid, as we are seeing the example, keeping on dilute and dilute, what we'll see? Concentration is becoming approximately 0. Then every electrolyte will act as a strong electrolyte. When alpha is 1, every electrolyte will be acting as a strong electrolyte. Now we'll talk about the temperature. The next point we're going to talk is temperature. So on increasing the temperature, whenever we increase the temperature, Ki increases and speed of ion also increases. Now Ki is increasing, speed of ion also increasing, due to which the constituent salt, acid, base, whatever it is, will be dissociating more into its constituent ion. So alpha will always increase. On increasing the temperature, the degree of ionization increases. Now there is a new term you will be learning here, that is known as common ion effect. So first of all, we will be learning what is the common ion effect. It has a lot of use in this ionic equilibrium. So first of all, what is this effect and when it is applicable? So this is applicable when minimum 2 electrolyte whenever minimum 2 electrolyte are present and are in same container and one ion means common, or we can say one common ion. Better it is one common ion is present in it. Means one common ion should be present in it. Let's take it by example. What is common ion effect? Let's say we have an acetic acid and HCl. HCl is a strong electrolyte and acetic acid is a weak electrolyte. Or we can say it is a strong acid, acetic acid is a weak acid. But they both gives the H plus. And let's say we have NH4OH and NaOH. Let's say we have acetic acid and sodium acetate. Let's say we have ammonium hydroxide and ammonium chloride. All these have some common ion. It also gives H plus, it also gives H plus. It gives OH minus, OH minus. It gives CH3CO minus, CH3CO minus. NH4 plus, NH4 plus. So, what after that? Let's say they have some common either cation or anion. So, now what after it? So, let's say we have some weak electrolyte present. Let's say AB, which will dissociate A plus and B minus. And we have another strong ion, let's say strong electrolyte AC, which will dissociate into A plus and C negative. So when they both are present in the same container, what will happen? The container doesn't know from where the A plus is coming. Is it is coming from AC or coming from AB? It will count all the A plus present in the solution. It will count all the A plus present in the solution. Now, whenever all the A plus is present in the solution, we know we have increased the concentration of product side. So, you can say whenever we have increased the concentration, Ki is fixed. Here we have A plus and B minus divided by AB. Ki doesn't change with concentration, it only changes with temperature. So whenever it is fixed, we are increasing the concentration. That means the concentration of AB will also increase to balance the Ki. So means the reaction will move in backward direction. So alpha of AB will decrease. Again, I am explaining. We have put it both the AB and which will dissociate into A plus and B minus, and we have put in the AC, which will dissociate, which will convert into A plus and C minus. It will ionize and it will convert. So if we write the equation Ki, it will give A plus B minus divided by AB. So we know Ki doesn't change with temperature, and you have increased the concentration of A plus because it doesn't know whether A plus is coming from this or this. It will count all the A plus that is present in the solution. So we have increased the concentration of A plus because it is common. It will count both the A plus. Now, to balance the Ki, the AB will also increase. Means the reaction will go in backward direction. You can keep it similar to like a Lee-Chatterjee principle, but that case was a little bit different. You can see the same case there. Like, okay, so on increasing the concentration of product, you will be seeing that the reaction will go in backward direction. Means eventually the alpha will decrease. So on having a common ion, the alpha will decrease. So depression of degree of dissociation of weak electrolyte due to the presence of a common ion produced from another electrolyte. It could be strong or weak. Doesn't necessarily both have to, one has to be strong or weak. It could be strong or weak. Is known as common ion effect. So where the common ion effect appear, so where do it work? So let's understand in a 2 point. First, common ion effect will work on, we can say, operate only for on weak electrolyte. It will not operate on strong electron because it has totally dissociated. Now how it can go back? So it will operate only weak electrolyte. Now second point is, higher the concentration of common ion, more will be the common ion effect, less will be alpha of weak electron. More than increasing the concentration of common ion, less will be the alpha.